All right, so this is Math 466, Lecture 10. So we're now going to pivot to Benford's law, and we're going to attack it by using some of the techniques from Fourier analysis. So we'll be moving to Chapter 9 now. We'll do some of the stuff from Chapter 9, and then I think from there we jump to Chapter 11. And there's going to be some results that we're going to need to prove, and we're going to prove them using Fourier analysis. Some of the stuff we can actually prove without using Fourier analysis. I found a better proof, and when Jay gave his colloquium talk earlier this year, he used the better proof. I still want to show the Fourier analytic proof because it illustrates some really nice concepts, and for some other problems, it's the way you have to go. I will still show the easier case, but it's nice to get a sense of what is needed to attack a certain problem. How far can you push something that's a certain amount of certain elementary techniques? Okay, so Benford's law. So I'm going to go really quickly through the basics here because you're supposed to have either gone to Jay's talk or watched the video, read the book by now, or you've probably, if you've taken probability with me, as everybody here has, you've seen a lecture on this, so we're not going to spend too much time. Benford's law is a law of digit bias. If you look at a lot of natural processes, yada, 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 you expect maybe 1/10 of the leading digits to be 1, 1/10 to be 2, 1/10 to be 3, and then you realize, oh, wait, we're not going to have any 0, so you correct to 1/9. And then it turns out about 30% of the time you start with a 1, and only around 4.5, 4.6% of the time you start with a 9. So the question is why? And so also, how do you attack something like this? Why is Fourier analysis so well suited for something like this? So let's say I give you a number. We'll assume we have a real number that's not 0. I can write this as the significand times 10 to a power. So for instance, 24601.1701 would be 2.46011701 times 10 to the 4th. I think 4th. Or, yes, right, to the 4th. So if I only care about the leading digit, I don't care about the k of x. I only care about the significand. And the significand will always be between 1 and 10. Of course, if we wanted to do this in a base other than 10, we would just change the 10 to base b and the subscript to b. So the first thing we want to do is we want to take a map from our number to the significand. And the nicest way to do that is we send x to the log base 10 of x mod 1. And the reason this works is when we take the log of this base 10, the log of a product is the sum of the logs, and then the log of 10 to the kx is just k of x. Well, k of x is an integer, so when we look at it mod 1, it vanishes. And because this number is between 0 and 1, so between this number is between 1 and 10, its logarithm will be between 0 and 1. So this lives in the interval 0, 1. Okay. Now, while it's convenient to do this, of course, in the real world, you will not view data like this. If you want to know someone's batting average, you're not going to take the log of the batting average mod 1. If you want to know what's the temperature outside, you're not going to do that. But for the analysis, this is very convenient. We now have a number on 0, 1, and we just spent a lot of time in the semester developing techniques to work on functions that are on 0, 1. So here is the fundamental equivalence. So here is the significance 1 to 10. Here's the log of the significance 0 to 1. So 10 to the 0 is 1. 10 to the 1 is 10. If I look at all the numbers that have a first digit of 1, they go from 1 to 2. 1 goes all the way down to 0 because I'm taking the log of 1 base 10. The log of 2 base 10 goes down to about here. And so all the numbers in here will have a first digit of 1. And since the log of 2 base 10 is about 0.3, this is where you get this 30%. So a data set is Benford if and only if the logarithms modulo 1 are uniformly distributed on 0, 1. And so the probability of a first digit of d would be the log base d of d plus 1 minus the log base 10 of d, which is the log base 10. The log of a difference is the quotient, is the log, I'm sorry, the difference of the logarithms is the logarithm of the quotient. So you get d plus 1 over d, and that's sometimes written as the log base 10 of 1 plus 1 over d. So these are the Benford probabilities. So if we want to show something is Benford, we just have to show that its logarithms mod 1 are uniformly distributed. All right. So then the question, of course, is how do you show that the logarithms modulo 1 are uniformly distributed? Basic probability. So f is a density if the following is true. F of x is greater than or equal to 0. The integral from minus infinity to infinity of f of x dx equals 1. We can talk about moments. The integral from minus infinity to infinity of x to the n f of x dx is the nth moment. For us, the most important density is going to be the Gaussian. So normal mean mu variance sigma squared, the density for that is going to be 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. And then the standard normal, the moments are the following. It's 2n minus 1 double factorial. 2n is even, and 0 for odd. So we proved this in probability. The double factorial means you take every other one and you stop either at 1 or 2. If you don't remember, it's a good exercise to prove and make sure you know how to prove that the moments are 2n minus 1 double factorial. And there's a nice combinatorial interpretation lurking here. Okay, so what we want to do now is we want to try to decide when is something going to be Benford. So we need to know when is something going to become uniformly distributed, mod 1. And what needs to become uniformly distributed is the logarithm. So the quick idea as to why so many things are Benford imagine we have some quantity yn, which is x1 times xn, product of n observations. Maybe they're identically distributed, maybe they're not. Simplest case is that they're identically distributed. Then the log of yn is the log of x1 plus the log of xn. If these are all IIDRV, then we have a sum of independent, identically distributed random variables. What should this converge to if things are nice? It should converge to a Gaussian. So the hope is that this becomes a Gaussian with standard deviation going to infinity, or variance going to infinity, because you're taking more and more terms. As you take more and more terms, the variance of the sum is the sum of the variances. So we want to look at a growing variance. Well, if you look at a growing variance, a Gaussian with a growing variance, we want to look at this mod 1. And it turns out a Gaussian with growing variance is going to converge to being a uniform. So think of it as this way. We have a Gaussian with increasingly large variance, and we're going to keep folding it over. We go from 0 to 1, and then we pick up what's going from 1 to 2, and we cut that out, and we put it right above the 0 to 1. And then we take what's going from 2 to 3, we cut that up and put that above. And we're going to add all the probabilities. Okay? The reason I want to do this proof is because this proof is going to show you why we were doing all the stuff we were doing in Fourier analysis. So let's say we have a random variable x, and we want to look at x mod 1. We'll call that y. So let's look at the probability that A less than equal to Y less than equal to B, that Y takes on a value between A and B. Well, this is the same as the probability that X mod 1 is in the interval AB, because Y is just X mod 1. So this is the same as the sum, and it goes from minus infinity to infinity, the probability n plus A. What do I want to do? A plus n. I'll do A plus n, I guess. A plus n less than equal to X less than equal to B plus n. So if you remember what we did before when we were looking at Poisson summation, we took a function and we said big F of x was the sum of little f of x plus n. And you can hopefully begin to see something like that emerging here. So this would be the integral. This would be the sum, and it goes from minus infinity to infinity, the integral from a plus n to b plus n, the density at x dx. Well, the density is positive, so I can switch the order of integration and summation. If it was infinite before, it's infinite already afterwards, right? There's no danger in interchanging orders here. You can always interchange orders if the integral of the absolute value is finite. Well, since it's a probability distribution, what's the sum of the probabilities? At most 1. So it's actually finite. So what we have is the probability that A less than equal to Y less than equal to B is equal to I will integrate from A to B of f x of, I'll do it in 2 steps. We'll have a sum, n goes from minus infinity to infinity, of x plus n dx. I'm just taking the n outside the bounds of integration. And so now all the integrals are from A to B. And now I'll move the summation inside, so it's the integral from A to B, the sum, and goes from minus infinity to infinity of fx of x plus n dx. And now you can see that this looks a lot like what we had before. If I had little x equals 0, it would be exactly the situation for Poisson summation. So the question is, how much of an error do we make if we just say, well, let's just replace this with, we'll assume there's no changing in each of these intervals. Well, you're going to make a mistake with that. But if the variance is getting larger and larger and larger, your function is not changing that much. And so the main reason I want to go through the rest of this proof is to just really hammer home some good analysis techniques. And just, how do you do something like this carefully? What are the issues? So if we didn't have that x here, we would just use Poisson summation. And then this would equal the sum over all n of f hat. So that means we're going to need the Fourier of a Gaussian if we're using a Gaussian here. For a lot of problems like this, you often want to split things into small n and large n. So we can break this into absolute value of n less than equal to, say, big N to the 5/4, and absolute value of n greater than equal to n to the 5/4. If our function has decay, well, since the sum converges, if we go pretty far down, it should be negligible. So what I want to do is we're going to prove some results first about Gaussians, about what is the probability that you're far away. So since you've all taken probability, whose theorem could we use? We could use Chebyshev. So Chebyshev would actually, I think, be strong enough for what we're doing here. We can actually do better than Chebyshev. Why does Chebyshev do such a crappy job? It gives really bad estimates. So for a Gaussian, say the standard normal, the probability you're 10 standard deviations away, according to Chebyshev, is at most 1 over 100. It is a lot less than 1 over 100. Why does Chebyshev do such a poor job? I mean, Chebyshev was a really nice mathematician. He's not a second-rater. It's because Chebyshev has to work for any probability distribution with finite mean and variance. So because it has to cover all of those cases, the bound it gives is weak. If we actually look at the fact that we have a Gaussian which is decaying damn fast, we should be able to do better if we actually use facts about this. So this is similar to what we did earlier with approximations to the identity and the Fourier kernel and the Dirichlet kernel. Sometimes we prove things in generality and said, oh look, if it's an approximation to the identity, we have this. Other times, we need to use the properties of what we're looking at. For the Dirichlet kernels, we needed to use properties of the Dirichlet kernel. And so here, we could just use Chebyshev, but let's do a little bit better. To make my life easy, I'm going to assume the mean is 0. That just translates things, not a big deal. So let's bound the integral of 2 over square root of 2 pi sigma squared, sigma 1 plus delta to infinity of e to the negative x squared over 2 sigma squared dx. So what am I doing here? I'm taking a normal, mean 0, variance sigma squared, and I'm looking at the probability of being at least sigma to the 1 plus delta away from the origin. How should you view, the 2 is because I have the negative side and I've just doubled it. How should you view sigma to the 1 plus delta? You should view sigma to the 1 plus delta as sigma to the delta times sigma. This is the standard deviation. This is the natural scale to measure my distance from the origin, from the mean. As sigma goes to infinity, this means I am many, many standard deviations away from the origin. And many is a function of...
As delta goes to infinity.
I'm sorry, as delta goes to infinity.
Yeah.
No, delta will be fixed. As sigma goes to infinity. As the variance gets larger and larger and larger. Okay? So the number of standard deviations we have is actually growing rapidly with sigma. Okay? So we want to show that this is small. All right, so the first thing we do is we do like a little change of variable. Let's let x over sigma equal u, so dx is equal to du times sigma. And so now we can change the integration. So I replace dx with du times sigma. That sigma cancels the sigma squared over here. We have a square root of 2 over pi. And now, when x is sigma to the 1 plus delta, u is just going to be sigma to the delta, going to infinity, e to the negative u squared over 2 du. And so we want to estimate this integral. So another way to try to estimate this is let's let u equal t plus sigma to the delta. And your t is going to measure how far away we are. So this is going to be the square root of 2 over pi. Integral t now goes from 0 to infinity. I'm going to have e to the negative t plus sigma delta squared over 2 dt. And if I expand out the exponential, the square root of 2 integrals, so square root of 2 pi integral 0 to infinity, e to the negative t squared over 2. Then the next piece is going to be 2t sigma to the delta over 2. So it's going to be negative sigma to the delta t. And the last piece is going to be e to the negative sigma to the 2 delta. And if instead of trying to do sigma to the delta, if we wanted to do 2 standard deviations or 10 standard deviations, you could do that here as well. You would replace sigma to the delta with 10. Why is this good? Where can you see decay? So we've got this expression. Where do you see some decay in this?
Oh, that's just a constant.
Yeah, we can pull this out. This can come outside the integration, and that means, well, we've already got an e to the negative sigma to the 2 delta. As sigma goes to infinity, that's going to go to 0 really fast. So that gives us great decay. How large are each of these exponentials?
The first one's small.
Okay. Well, the first one might not be small. If t equals 0, the first one is just e to the 0.
Right.
How large is each exponential? In absolute value, how large is each exponential?
Like at most?
At most.
1.
So each exponential is at most 1. We could actually integrate either, so we could drop one of them and just concentrate on the other. If we concentrate on just this one, we're integrating an exponential. We would multiply by a sigma delta, sigma to the delta, and divide by sigma to the delta. So the integral of just this would be like 1 over sigma to the delta. If we wanted to integrate this, that's close to just integrating a Gaussian. That would integrate to 1. So in fact, a really good bound for this is to say, screw the Gaussian part, replace it with 1, have the exponential. That'll get you an extra 1 over sigma to the delta. And that'll get this whole thing is bounded by square root of 2 over pi. And then down below, we'll have a sigma to the delta, and we'll have an e to the sigma to the 2 delta. So it's enough to show that it's really small. And again, what I like about this is just the techniques to handle integrals like this and to approximate, is you want to move it to where's the action happening. So I'm starting off by integrating from sigma to the 1 plus delta to infinity. Let me adjust my variables a little bit. So I've adjusted them. And then really, once u starts getting far away from sigma to the delta, it's going to become very, very small. Most of the action is happening at the smallest value. That's the whole point here. It's basically when t equals 0, that's where the meat is. And so we are able to isolate out that t equals 0 piece right here, pull that out. And we can actually get even a little bit more decay if we needed it from this. So this tells us that the integral of a Gaussian from sigma to the delta to infinity is going to 0 really fast. Okay. Any questions on this calculation? Okay. So what we need now is we are going to look at the following. And I'm going to just check my notes because otherwise I will have the wrong normalization. And so what I want to do for my Gaussian today is 1 over square root of big N e to the negative pi n squared over n has Fourier transform e to the negative pi. I'm pretty sure this is a typo. N squared n. Okay. This is not written in the standard form where we have, negative x squared over 2 sigma squared. So basically for this one, we want negative pi n squared over n to equal negative, n squared over 2 sigma squared. So sigma squared would be what? It would be n over 2 pi. And then that's why the 1 over square root of 2 pi sigma squared is giving us a 1 over square root of n. So I'm just choosing my Gaussian to have variance n over 2 pi. And I'm going to let sigma go to infinity, so that's the same as n going to infinity. You just want to get a sense of what the scale is. The whole point is it just makes using the Poisson summation formula a little bit nicer. The Fourier transform is going to go like this. We have not calculated the Fourier transform of the Gaussian. It would be so nice if you guys had taken complex analysis right now, because then we could use complex analysis to compute the Fourier transform, because we'd be integrating against a complex exponential. This is precisely why you have classes like complex analysis. So I thought a little bit this morning, it is possible to calculate the Fourier transform of the Gaussian without using complex analysis. So I will leave that as a challenge problem for you guys to think about over the weekend. How can you do this? Because it's fundamentally, it involves complex analysis. How can you do this? So you would want to integrate from minus infinity to infinity 1 over square root of n e to the negative pi x squared over n e to the negative 2 pi I xy dy. That's what you want to evaluate. And you can do it without using complex analysis. There's got to be multiple tricks you need to do. You've got to use some algebra right. You've got to find the right perspective. But I'll leave that as something for you to think about. All right. So let's go back to the probability that our variable is between a and b. And so we're going to assume y has this as its density. So we'll assume that this is the density of y. Y is a normal with mean 0 and variance n over 2 pi. And we're going to be looking at the case as big N goes to infinity. All right, so when we're looking at this, we know that the probability becomes damn small if we go a little bit more than the variance. And now you can begin to see why I'm choosing n to the 5/4. Because you can view n to the 5/4 as basically n to the 1/4 times n. That's essentially my variance. My delta is basically equal to what? 1/4. Is this exactly what I did? No, there's this damn factor of 2 pi. I don't care. Right? It's not going to really matter. You can adjust things. The main thing is I've gone a good distance away. And so if we look at this, if I chop off the sum and throw away all the n greater than or equal to 5/4, it's going to be extremely small. So I'm integrating from a to b. I make the integrals larger if I go from 0 to 1. So for the n greater than or equal to 5/4, send ab to 0, 1. And you can bound by essentially square root of 2 over pi times some constant, because I screwed up with the pi's earlier, divided by sigma to the delta. So we'll have n over 2 pi to the delta e to the n over 2 pi. Oh, wait, it's sigma to the delta. So I think this should be to the delta halves here, because sigma is equal to n over 2 pi. I'm sorry, sigma squared was equal to n over 2 pi, so sigma would be the square root. And then this would be n to the 2 over pi to the delta, something like this. This is extremely small. So you just have to go through it carefully, but what it's saying is, look, the variance is n. You expect things to be small once you get to, the standard deviation. We're going way beyond that. It should be damn small. And so, actually, so let's see how I want to do this. Or did I screw up? Do I want it? Because we want to go to the standard deviation to the 1 plus delta. And the standard deviation here should be, the standard deviation should be n to the 1/2. Right? I wrote it the wrong way. Right, the standard deviation should be n to the 1/2, because sigma squared is n. So sigma is n to the 1/2 roughly. So this would be n to the 3/2. Right. Sorry. So it would be 5/4 minus 1/2. It's 3/4. Right. And so if we want to write this, we should write it, carefully as sigma squared is n. So n is 2 pi sigma squared to the 5/4. This would be 2 pi to the 5/4 sigma to the 5/2. So this would be 2 pi to the 5/4. We want a sigma, and then we'll be left with sigma to the 3/2. So we are really far away from a standard deviation. So from a Gaussian, if you're even 5, 6 standard deviations away, it's small. If you're log n standard deviations away, it's small. This is a lot more than that. We are so deep down that those values don't really matter. So is everybody comfortable that we can replace this with absolute value of n is less than or equal to n to the 5/4 plus something really small? And in the book I go through and I bookkeep as to what that very small is. So we're all comfortable with this? So now we have a finite sum. And what I want to do for the finite sum is I want to see what's the harm in replacing x plus n with just n. Okay? So that's what we need to look at now. So we no longer need this bound. So we want to look at absolute value of n is less than or equal to n to the 5/4. And we want to look at f of x plus n minus f of n. We want to see how much of an error do we make. How could we try to approximate the error? F is the density of the Gaussian. So what could we use to try to approximate f of x plus n minus f of n? We've used this before. We used this in proving Poisson summation. You have a difference of a function at 2 points. What could we use? One of the big theorems from calculus.
MVT?
Yeah, mean value theorem. Whenever you see the difference of two functions, especially if the function's not changing that much, if the function's not changing that much, what can you say about the derivative? It should be small.
Yeah.
So this should just be f prime at, say, some intermediate point. And then what's the distance between them? The distance between them is x. So we just need to show that this is small. All right, so f, I'll use the letter u now, is equal to 1 over square root of n e to the negative pi u squared over n. F prime of u is going to be, when we take the derivative, we get the function back, and then we have the derivative of this piece. So we'll get negative 2 pi u over n f of u. So now we can begin to see why I wanted to make some kind of condition on how large n is. That's going to control how large this number is over here. Now, I'm evaluating this at an intermediate point. I'd love to evaluate it at 0. So maybe instead of doing the mean value theorem, maybe it's better to do a Taylor series expansion. F of x plus n is f of n plus f prime of n times x plus f double prime of n over 2 factorial. So it's always a question of how do we want to attack? How do we want to approximate? And so the nice thing about doing a Taylor series like this is the point I want to replace it with. I want to replace f of x plus n with f of n. F prime, I'm evaluating it at the point n. And then it's getting smaller and smaller. So it all comes down to which is going to lead to the better algebra. And until you do these problems many times, it's not clear which is going to lead to the better algebra. This is why I want to show you both of the ways and try to think, how can we approximate things? How can we bound things? The other thing which is important to note for this problem is the difference is going to be a nice multiple of the value itself. Now, because my function is decaying, the largest value for this is going to be basically the smallest value of u. The larger I make that, the more decay I'm going to have in f prime. So we can get that the absolute value of f of x plus n minus f of n is going to be less than or equal to 2 pi absolute value of some point Cn plus n over n. And then the largest this will be is if we assume Cn equals 0. So it'll be e to the negative pi n squared over n divided by square root of n. And in fact, the largest it would be is if we put a 1 there. Right? I'm just doing the worst possibilities. If you wanted to, because little n could be negative, maybe there's a shift of n plus 1. We'll just do the things for the positive n. You can do the other ones similarly. The point is, even though I have an n over here, I have so much decay over here that it's not going to matter. And so now we want to just see what's going to happen if we deal with the error terms. So, well, I'm not going to bother going through showing that the sum of this over little n is small. You need to just evaluate basically the sum, absolute value of n less than or equal to n to the 5/4 of n over n e to the negative pi n squared over n over square root of n is small. I'll just say a few words as to how you would show that this is small. When I'm trying to do the approximation, I have to worry a little bit about what happens if little n is very, very large, because this is getting very, very large. But if little n is getting large, then this term is really, really small. We could extend this sum all the way to infinity. And then this is essentially like, it's not quite the mean because we have an absolute value, but you could almost bound it by the variance. You put this in as an n squared. And what's really nice is the absolute value of n is always less than equal to the absolute value of n squared, is always less than equal to n squared. So I could say it would be less than equal to essentially n squared. And now, oh, this looks like the variance. But this square root of n is needed for the variance calculation, and we have an extra 1 over n lurking. So this would be bounded by like the variance over n. How large is the variance? I'm sorry? The variance is going to infinity. But the variance is n over 2 pi. So if we put the variance as n over 2 pi, we just lose. We just lose. This number is just a little bit too large. Because this number is now of size 1. It's not going to 0. Remember, the variance is of size n over 2 pi. So if we're so crude as to replace n with n squared, we're in trouble. All right, so what that means is, well, we're in trouble with that. If we don't replace n with n squared, if we just stick to like this, we should be okay. And I'll leave this as you can replace the sum with an integral, integrated like x e to the negative pi x squared over n, and then just bound that. You can actually just integrate directly, right? Because now you want an n with an n squared, or an x with an x squared. So it's always nice to see, can you do a crude estimate? The crude estimate sadly just failed. It got us to something that was of size 1. So we have to be just a little bit more clever, but not much. And so you'll bound this with something like 1 over n to the 3 halves integral, and you'll have to figure out what the bounds are, something like x e to the negative pi x squared over n dx. All right, so now we can come back over here, and now that we've shown that those bounds are small, we come back over here, we threw away the contribution from all the large n's, and now we can remove the x inside at a cost of small error. So now it's a new small error. Now we can extend the sum to being over all n for another new small error. So if you want, we went now to small error sub 3. This is our third small error. And the reason is the function has such rapid decay that putting back all these extra n's now doesn't matter. Now, what should we use to evaluate this infinite sum? Now we use Poisson summation. And so now this is the integral from a to b of the sum, and it goes from minus infinity to infinity of fx hat of n dx. It's also pretty easy to do the x integration because there's no x dependence in the integrand. So you get b minus a, and then you get a sum, and it goes from minus infinity to infinity, and now we put in the Fourier transform is e to the negative pi n squared n. So we get e to the negative pi n squared big N. Okay, we're almost done. All right, we've got hopefully about 5 minutes left. Yeah, we'll just make it. The amount of detail I'm doing in the calculations is designed so we essentially hit the buzzer when the class ends and we get through the main stuff. You don't want to break a long algebraic proof into 2 lectures. So let's look at what Poisson summation was telling us here. It was telling us that 1 over square root of n, e to the negative pi n squared over n, sum over all n, is the sum over all n of e to the negative pi n squared n. If you look on this side, when the absolute value of n is less than or equal to square root of n, this is essentially e to the 0. And all these terms contribute. So you're going to have a long sum of things that contribute. And then once little n is greater than square root of n, like maybe square root of n log n, it's now going to be small. On this side, what contributes on this side? Where's most of the contribution?
Big N.
I'm sorry? We have an e to the negative pi little n squared big N. So for which values of little n is this large? So on this one, which value of little n gives you most of the contribution?
It's going down from negative infinity to infinity.
Yep. And big N is huge. So which value of little n has most of the contribution here? In this sum, little n goes from minus infinity to infinity. What value of little n has this large? 0. When little n equals 0, you get 1. So this is 1 plus now a sum, absolute value of n equals 1 to, well, let's just say n equals 1 to infinity, and we'll double it, e to the negative pi little n squared big N. Imagine big N is a googolplex. 0 times a googolplex is 0. 1 times a googolplex is a googolplex. 4 times a googolplex is 4 times a googolplex. All of the other values of n give an incredibly small contribution. So basically it's just 1. And in fact, we can approximate this. This is going to be less than or equal to 2 times the sum, and it goes from 1 to infinity of e to the negative pi n. Right? Because I'm making the exponents smaller, so I make them all larger. This is a geometric series. So it's going to be 2 e to the negative pi n, 1 over 1 minus e to the negative pi n. And you can see this is exponentially small. This is the power of Poisson summation. Is you go from having to deal with a long sum of a lot of different terms that are contributing to basically just one term contributes and throw the rest away. That's an incredible power Only one term matters. So now, if we go all the way back to here, this is going to be the first term is just b minus a plus, oh, and I still had plus my small, plus now a new small 4. Because I'm going to have an exponentially small error term. And so what we've just shown is that the Gaussian, with increasing variance, when you look at it mod 1, it really is converging to being uniform. So if you want the central limit theorem for sums of logarithms, mod 1, is that it converges to the uniform distribution. That's the limiting distribution, not the Gaussian. Or the Gaussian mod 1, as the variance goes to infinity, becomes the uniform. There is an enormous amount of algebra that we've done here today. It's worth going through it slowly. Look at the book again. Look at the notes. Trying to understand how do we make these estimates? How do we break things up and say, where's this large, where's this small? This is also to make you really appreciate the other way to prove this that I showed Jay, which allows you to bypass all these estimations, all this calculus and whatnot, and show that it converges to uniform. I wish I had thought of this earlier when I was writing the book. I apologize. But this is the advantage of teaching a class versus writing a book, is you can revise your lecture notes a lot more readily than you can. So what I will end you with is I want you to calculate, so this is your assignment. Find the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative, x squared over 2 sigma squared, e to the negative 2 pi I xy dx. And I should have, I guess, a sigma squared here. So this is the Fourier transform of a Gaussian with mean 0 and variance sigma squared.
Shouldn't be dy?
No, I'm integrating out x. And this is giving me a function of y. If it was dy, then the Gaussian over here would have no dependence. So the Fourier transform is, the integral of f of x e to the negative 2 pi I xy dx. And that will give you a function of y. So can you evaluate this integral? You do know enough to do it using just real variable techniques. You do not need to know complex analysis. It's a lot easier with complex analysis. But it can be done. So try to think about how you would evaluate that. This is one of the key ingredients. If we're going to use something like Poisson summation, we need to know Fourier transforms. We need to be able to compute things like Fourier transforms. And we want to be able to pass back and forth between these different spaces. So for some things, the Fourier transform is easier to work with than others. We'll probably circle back to the central limit theorem later in the course. The Fourier transform converts convolution to multiplication. The Fourier transform of a convolution is the product of the Fourier transforms. Well, what that means is since convolutions gives us the sums of density functions, if I have a sum of a bunch of variables that's a convolution, I take the Fourier transform that's now a product, I can work with products a lot better than I can with integrals. I then solve things for the Fourier transform, and then somehow we invert. The inversion is not always easy. But, all right, so this was a technical lecture. Every now and then you have to have the technical lecture, but it's designed to show you why the stuff we've learned is useful.